Darya Kaviani, speaking about Flock, a framework for deploying on-demand distributed trust.
Hi, everyone. My name is Darya, and I'll be presenting our work Flock, a framework for deploying on-demand distributed trust. This is joint work with Sijun Tan, Praveen Govindan-Kannan, and Raluca Adapopa. So what is distributed trust and why is it useful? Well, suppose a user, Alice, has a secret to store. She can store it on a server, but what if that server is malicious or compromised? In this case, the server is a central point of attack. Enter distributed trust. Under the distributed trust paradigm, Alice splits her secret into several pieces and distributes it among several parties. In this case, distributing the sensitive data avoids a central point of attack because adversaries must now compromise all N servers in order to compromise the secret. So even if one server or even up to N-1 servers are compromised, Alice's secret is still safe. Many distributed trust applications are enabled by a cryptographic primitive called multi-party computation, or MPC, where several parties are going to compute some joint function f on their inputs, and the key property of MPC is that the parties do not learn anything about each other's inputs other than the final function result. A key example of the need for distributed trust is in the application of digital asset custody, where a user, Alice, has maybe the Coinbase wallet application on her client device, as well as a signing key that she uses to sign transactions and, say, post them to a blockchain. But this begs the question, where can Alice store her transaction signing key? Unfortunately, to date, billions of dollars have already been stolen by compromising these very signing keys alone. That's why many of these applications have already turned to distributed trust, where Alice is going to instruct these parties to conduct an MPC for signature key generation in order to produce shards of the signing key. Next, when Alice wants them to sign a transaction, she's going to send copies of it to each of the parties. Next, they're going to engage in another MPC in order to produce a signature on the transaction. And finally, as usual, the transaction can be posted. Even if one of the parties is compromised, the secret share reveals nothing about the overall secret, and so Alice's secret is still safe and the system doesn't have a central point of attack. And this is just really the tip of the iceberg. We actually manage a growing community-owned hub of MPC applications at mpc.cs.berkeley.edu. So there are a lot more distributed trust applications, but unfortunately, a significant challenge still precludes the mass adoption of distributed trust. And this is that a large class of prior work simply assumes that N non-colluding trust domains already exist. But this is far from the truth. And it brings us to the deployment dilemma, which is how can an application provider, which is inherently a single trust domain, go ahead and deploy a multi-trust domain system? So let's give this a shot. For our first attempt, we'll just have the application provider deploy N servers. Okay. And then Alice is going to share her secret and distribute it among them. But clearly, if the application provider is compromised, then so are all of the parties that it deployed. So this clearly won't work, and it brings us to today's model of traditional distributed trust, where the application provider is tasked with forming business relationships with N-1 other entities. But unfortunately, this has been pretty tricky in the real world. Whether it's Meta's private advertising, Signal's secret key recovery, Google and Apple's private analytics, or Coinbase's digital asset custody, real-life deployers of MPC have found that it is difficult to convince MPC parties to deploy, run, and maintain your application workload. And so imagine how hard this is for your everyday application developer. And so our goal in this work is to enable anyone to automatically deploy distributed trust, even just a single developer. And so the key insight of our work is to fundamentally rethink how we think about distributed trust deployment. Because in the traditional model, it's the application provider's job to find the parties, form the business relationships, deploy the code, and then the user, Alice, is going to interact with the parties. We propose the following alternative. Yes, the application provider can run a party, but the user, Alice, is the trusted owner of her own sensitive data. And so she can actually help with the conducting of her deployment for the other N-1 parties. And this results in an automatic deployment paradigm that we call on-demand distributed trust. Our system Flock is for deploying on-demand distributed trust through user-driven deployment by using cloud providers as trust domains. So first, we'll discuss how we reverse the approach to deploying distributed trust by taking the onus from the application provider and leveraging the user at the core of the deployment. And second, we'll show how we design a practical end-to-end system to realize this vision in a way that's both cost-efficient and secure. We also port 8 different distributed trust applications spanning 5 core cryptographic modules in our work, and you can learn more about these in our paper. So before we dive in, we'll discuss who we can trust and who we can't. A key assumption of our work is that at least one cloud server is uncompromised. We would hope that AWS, Azure, and GCP don't all get attacked by the very same attacker at the very same time. Also, we have malicious security if the application that's deployed on top of Flock is also malicious secure. We assume that client code is trusted because we assume that code is open source and therefore community scrutinized. And a nice property of our model is that compromised clients cannot affect uncompromised clients. Okay, so how do all of these pieces come together? Well, for our first try, let's just have Alice, the user, deploy n-1 VMs in n-1 distinct clouds. And the application provider can do an MPC execution with these VMs. Unfortunately, we run into a bit of a scale issue because this might work great for one Alice, maybe even 2 Alices, maybe even 3, 4, 5, 6, or 7 Alices, but try tens of millions of Alices or the number of monthly active users of an application like Coinbase. So the harsh reality is that 1 VM per user per cloud is just going to be prohibitively expensive for these ephemeral workloads. To solve this problem, we turn to serverless computing in order to scale Flock. Serverless computing is stateless compute that exclusively incurs costs at execution. Unfortunately for us, most major cloud providers offer a serverless computing offering. There's 2 really great things about serverless that are great for Flock. The first is that serverless incurs no cost when the user is not actually performing an operation, and serverless containers are executed on demand with very low startup time. So how would this work? Well, the Alice is going to go ahead and deploy S1 and S2 serverless instances in distinct cloud providers, and the application provider is going to do the MPC execution. To make this more concrete, maybe Alice deploys an AWS Lambda instance and a Google Cloud Run instance, and the application provider can run in the other cloud, Azure. But this brings me to our first main technical challenge, which is that in MPC, you need the parties to be able to communicate over a secure connection. But unfortunately, serverless instances, especially those in distinct cloud providers, do not inherently accept incoming connections because they're in distinct network address translations. And so our question was, how can we establish secure peer-to-peer serverless connections? The insight here is that, yeah, we can't trust the application provider for security. That's the whole point of this work, but we can trust it for availability because it is the entity that wishes to offer this service. So what we do here is we actually leverage the application provider to run an untrusted relay to securely route messages. And this solves our connectivity issue because the serverless instances can just connect to that central relay. And so we have to actually create a new 2-phase TLS establishment protocol that allows us to establish an end-to-end secure TLS connection over 2 consecutive TCP sockets. Great, so we've solved our connectivity challenge. We can now do MPC among these different serverless instances. The second main technical challenge of our work was in authentication. As you can see, the system architecture we have on the right here is far more complex than your standard application. And the problem is really that user-driven distributed trust introduces new attack vectors all across the stack. So the question we have to answer now is, how can a provider secure a deployment it just doesn't control? So like a usual application, an attacker could attack at the application level. But in our case, it can also attack at the cloud level or at our more complex network connections. So our task was to design a comprehensive authentication suite sort of spanning all of these layers. To secure the application layer, we used MPC Auth, which is a cryptographic protocol that allows a user to authenticate to n parties with the work of 1. To secure the cloud layer, we used cloud IAM access keys for invocation purposes. And for the network layer, we used certificates. So parties authenticate with user-signed certificates to one another whenever they're forming their network connections. And another challenge that you can read more in our paper about is in resource protection. So how can the provider protect the deployment without controlling it? And for this, I encourage you to take a look at our paper. Great, so now that we've solved the main challenges, I'd like to bring us to the original example of digital asset custody to see how all of these moving examples come together. Recall that we have a user, Alice, with a signing key, and she wants to sign a transaction and post it. How can we do this with Flock? Well, first, The application provider is going to go ahead and provide the code to the user's client device. Next, the user is going to programmatically deploy the application in serverless instances S1 and S2. She's going to take a PIN that we'll later use for authentication and distribute it among the parties. Next, we're going to have these parties engage in the MPC we talked about earlier for the signature key generation, so they now have shards of the signing key among them, 2 of them at the serverless, and 1 of them at the application provider's VM. Now Alice wants a transaction signed, so she's going to take a PIN attempt, which should be equal to the original PIN, split it into pieces, and distribute them among the parties. Next, they're going to engage in an MPC over their secure connections for an MPC auth to check whether the PIN attempt is equivalent to the original PIN. And if it is the case that this check goes ahead and passes, now Alice can send her transaction over to the parties, and then they're going to engage in an MPC in order to do the signature generation, and we're done. We now have a signed transaction, and we've successfully used Flock. To make this crystal clear, I'll also give us another example with another example application of secret recovery. So what is secret recovery? Well, in many end-to-end encrypted applications like Signal, a user Alice downloads the app, and say another user Bob does the same. And what they want is to have an end-to-end encrypted communication channel where they can send messages back and forth. And so similarly to our other application, this begs the question, sort of where can Alice store her encryption key? Well, she could store it on her client device, but what happens if that device is lost, stolen, or broken? I mean, she could store it on the server, but again, that server could be malicious or compromised. She could also have another alternative where she encrypts it with a 4-digit PIN, sends that ciphertext over to the server, gets that ciphertext back, decrypts it with a PIN attempt, gets her key, but this is susceptible to a brute force dictionary attack. So as an alternative, I'll propose that we use Flock for this. So how can we do this? Well, first, Alice is going to get the code from the application provider. So in this case, Signal is going to somehow provide the code to Alice's client device. Next, she's going to programmatically deploy the application to serverless instances S1 and S2. She's going to take both her PIN and her secret key, distribute it among the parties. And now, suppose that she wants to reconstruct her key. She's going to take her PIN attempt, split it into several pieces, distribute it among the parties, and then again, they're going to establish their secure connections and do MPC auth to see whether the PIN attempt is equal to the original PIN. And if the check passes, Alice can successfully recover her key. Now we'll talk about our implementation and evaluation of our system. So starting off with the implementation, like I said earlier, we implemented 8 different distributed trust applications spanning 5 core fundamental cryptographic modules here. This was implemented in 2,000 lines of Go, Python, and C++ each. And for our evaluation, we really wanted to ask, is Flock's performance comparable to traditional distributed trust? What is the downside of using Flock? Is it the same as before? And so for the baseline, we deployed VMs on the distinct cloud providers, one in Azure, one in AWS, one in GCP. And for Flock, we deployed the application provider in Azure and then serverless instances in the other 2 clouds. Overall, we found that our latency on average across all of the cryptographic modules we evaluated was about 1.05x the baseline. And it was quite a similar story for the throughput. So we saw that we had comparable throughput across the board with these different applications. We also conducted a cloud cost comparison to see the dollar cost difference for an application provider. So this was a bit tricky because in terms of a cost model, VMs have a fixed hourly cost, whereas serverless cost is actually per request. And so we actually estimated the server's per request cost from the module's maximum throughput. And these were our results. You can see that for signing an application that is a bit more compute intensive, because there's an upcharge for serverless compute on the clouds, there was about a 2.5x cost overhead, but something like decryption, which is more network intensive, was only 1.3x overhead. But what I'd like to emphasize is that this cost, Flock's system cost overhead, is really negligible when it comes to the cost of setting up these business relationships. So if you ask any of the MPC deployers in the room, I'm sure they'd tell you that they'd rather spend a little more cloud cost money and solve the non-collusion problem. So zooming out to a bird's eye view of Flock, Flock combines the security of the clouds and reverses deployment to leverage users at the core of the system. And in doing so, we provide the first way for an application provider to automatically and immediately deploy distributed trust. Here's where you can learn more about our paper as well as our code, and I'm happy to answer any questions.
We have plenty of time for questions.
Thanks for the talk. So, okay, you illustrated a scenario where Alice is a customer of, I guess, Coinbase, roughly, right? But Alice now presumably also needs to be a customer of like AWS in order to deploy Lambdas, right?
So she's going to have to, basically the way that our system works is we use a web page automation framework so that the client device sort of takes one password and then automatically navigates the creation of the different cloud accounts and programmatically deploys the serverless instances. So yes, she will behind the scenes have an account with the cloud providers, but it's not like she's going to have to go manually set up that process on her own. We actually integrated this and have, the multi-factor authentication for the cloud providers built in.
And a quick second one is, am I right in thinking that this setup rules out secure aggregation?
Yeah, so we really outlined in our paper, but the distributed trust applications that this works for are those in two categories. One, where the sensitive data is owned by one user, or if you're computing on public data. So this would work fine for PIR on a public database. It would work great when there's like a secret key. Maybe you're doing like a collaborative kind of snark or anything where the secret sensitive data is that of one user and the MPC is for one user. But like you're saying, when it comes to something like private analytics, the sensitive data is the combined data of all the different users. And so that's actually a problem that, we're still thinking about how to solve in an on-demand deployment model.
Thank you.
Thank you for the talk. Could you elaborate on that line of NAT between the two serverless functions and two different cloud providers? Because typically you would run these things behind API gateways, in which case they can just talk over TLS.
Yeah, so we actually found that, the different cloud providers, we were able to do a sort of TCP hole punching approach to get Lambdas within the same cloud to communicate, but we found that, there's kind of some NAT and firewall configurations that are not exposed to end users. So using a more direct approach to establish those connections was quite difficult across clouds. And so in order to provide a solution that was really foolproof and could work across the board, any cloud, any sort of NAT configuration, any firewall configuration, we opted for the relay. But you could definitely have another way. It just might not be as general as the relay approach.
Thank you. And sorry, a quick follow-up question. Do you consider relaxing your threat model a little bit, say, to a single cloud region being attacked? So you could actually do this within one cloud provider?
Yeah, so, if you trusted the fact that, if you consider the different AWS regions as different trust domains, then you could totally do that. And maybe it would make the networking not require an untrusted relay or something of the sort. But we thought it would be stronger to say, okay, let's make it the case that Azure, GCP, and AWS, all three of those are not going to go out at the same time. But yeah, if you wanted to consider the different regions as different trust domains, then you could do that.
Thank you.
Hi, great talk, and thank you for the talk. I have a question. How did you actually measure the latency? Because like in my opinion, if you deploy a new function for every transaction, doesn't that require additional latency that is significant for every transaction?
Yeah.
Or how did you kind of measure the latency itself?
Yeah, so we actually don't deploy a new function every time. So when you are setting up the system, in the very beginning, Alice is going to programmatically deploy the serverless instances. But later on, because we have all these authentication layers, you actually use the previously deployed instances and you just invoke the serverless instances. Now, there are challenges with cold start, which is why we have to use, specific, we couldn't use things like AWS Fargate, which have like a slower startup time. And that's also why we had 1.05x the latency. It's a little bit slower, but you're not deploying every time. You're invoking every time.
Oh, okay, thank you.
Yeah, of course.
One last question.
Yeah, sorry. In the Signal example, what happens to the cloud credentials if I lose my device? Like, do I need these to re-authenticate, or are those stored somewhere else?
Yeah, so at the cloud layer, we really wanted to prevent a situation where an attacker who doesn't have the application layer authentication factor just would drain funds by just invoking the instances. So we do have that cloud layer of authentication. It's one of our 3-tier authentication factors. And if you lose that, then you do need to go through the cloud and re-download a new one.
Okay, so in a certain sense, you're partially depending on the cloud for your security model there.
So not necessarily, because even if that was compromised, you're still not going to be able to get into the application because you still have the application level authentication.
Assuming you can't.
But if you lost your device, you would need to just, get a new IAM access key.
Okay,
Yeah.
thank you.
Let us thank the speaker again.